Topic: Advanced emerging technologies for software engineering for classical and quantum computing. Software engineering is undergoing a fundamental transformation shaped by advanced emerging technologies that blend artificial intelligence, automation, and quantum computing. Traditional methods based on deterministic logic and sequential life cycles are evolving into intelligent, autonomous, and quantum-aware ecosystems. In both classical and quantum computing, software engineering now extends far beyond code efficiency or architecture design. It involves self-learning systems, AI-assisted development, automated verification, and hybrid orchestration between classical processors and quantum hardware. These innovations enable adaptive and evolving systems capable of meeting the immense computational demands of modern society. The discussion that follows explores the conceptual foundations, principles, algorithms, and practical implications of this new generation of software engineering for the classical and quantum domains. Conceptual foundations. Advanced emerging software engineering refers to the integration of intelligent automation, machine learning, and quantum computation throughout the software lifecycle. It incorporates reasoning, perception, and learning into the act of designing and maintaining code. Key conceptual pillars include cognitive software design supported by AI, quantum-ready architectures capable of exploiting superposition and entanglement, hybrid classical quantum systems that operate seamlessly across heterogeneous computing layers, autonomic lifecycle management using feedback from performance data, and responsible engineering practices embedding fairness, transparency, and energy awareness. These ideas collectively reimagine software engineering as a continuously learning system rather than a fixed production pipeline. Justification and importance. The movement toward intelligent and quantum-aware software engineering is driven by several pressing needs. Complexity management has become critical as digital ecosystems expand in size, interconnection, and data intensity. AI-driven co-engineering provides a means of handling this complexity while maintaining reliability. The quantum transition adds another layer of urgency. Quantum computers require new abstractions, algorithms, and verification paradigms. Their probabilistic nature makes classical approaches inadequate. Automation and efficiency are equally compelling motives. Industries demand faster development, continuous delivery, and near-zero downtime. Intelligent automation and self-optimizing life cycles meet these expectations by introducing adaptability and predictive maintenance into the software process. Ultimately, adopting advanced emerging technologies ensures competitiveness, sustainability, and innovation capacity across the technological landscape. Core engineering principles. Intelligence and adaptivity lie at the heart of the new software paradigm. Development tools now include AI reasoning engines that analyze requirements, generate code, and detect anomalies autonomously. Abstraction and interoperability allow classical and quantum components to communicate through layered middleware and cross-domain APIs. This ensures smooth operation across CPUs, GPUs, and quantum processing units. Continuous learning and evolution mean that deployed systems collect performance metrics and feed them back into the engineering cycle, producing self-optimizing behavior over time. Verification and explainability are increasingly vital. Because emerging technologies involve probabilistic computation, correctness is validated statistically and logically, often supported by explainable AI frameworks. Ethical and sustainable design completes the picture by embedding transparency, privacy protection, and energy-aware computation into the foundation of software systems. Advanced techniques in software engineering. AI-driven design automation uses machine learning models to generate architectures by analyzing system behavior and performance history. Generative design assistants can translate natural language specifications into modular microservice blueprints. Agentic collaboration systems employ multiple autonomous agents that handle design, testing, and documentation through cooperative reasoning protocols. Frameworks such as Meta-GPT and SWE-Agent demonstrate how distributed intelligence can perform large-scale engineering tasks collectively. Quantum-aware compilation and testing introduce noise-tolerant compilers, error mitigation strategies, and quantum debuggers that preserve circuit fidelity on imperfect hardware. Self-healing and self-optimizing systems detect runtime anomalies and automatically adjust parameters or configurations. They represent a practical step toward fully autonomic computing. Hybrid DevOps pipelines link classical continuous integration systems with quantum cloud orchestration, distributing workloads intelligently between conventional and quantum resources. Algorithms and frameworks. Artificial intelligence algorithms for classical software engineering include transformer-based models that understand and generate code, reinforcement learning agents that optimize deployment performance, and graph neural networks that map dependencies and vulnerabilities within large codebases. Quantum algorithms expand the engineering toolbox. Quantum search methods accelerate debugging and test generation. Quantum annealing assists in scheduling and resource optimization, and variational eigensolvers model system performance landscapes. Hybrid AI quantum approaches bring together the two worlds. Machine learning is used to configure and optimize quantum circuits, while quantum kernels enhance classical data analysis and pattern recognition, forming feedback loops between AI and quantum computation. Tools and platforms. The ecosystem supporting advanced emerging software engineering spans both AI and quantum technologies. AI-augmented development environments such as GitHub Copilot, Gemini Code Assist, and Tab9 automate code creation, testing, and documentation. Agentic engineering systems, such as AutoGen, LangChain agents, and Meta-GPT, coordinate multi-agent collaboration for design and validation. Quantum development kits, including IBM Qiskit, Google Cirq, Microsoft QHash, and Xanadu PennyLane, provide resources for circuit design, simulation, and hybrid experimentation. Hybrid orchestration services such as AWS Braket, Azure Quantum, and NVIDIA CUDA Quantum manage distributed execution across diverse computational substrates. Verification and simulation platforms, such as QTIP, QVerify, and TensorFlow Quantum, among others, offer tools for analyzing errors, modeling system behavior, and integrating AI with quantum logic. Together these technologies create a comprehensive AI quantum software ecosystem. Reinventing the software engineering lifecycle. The traditional software lifecycle has evolved into an intelligent, adaptive framework, sometimes referred to as the quantum-aware or cognitive SDLC. During requirements analysis, AI interprets human objectives and translates them into formal specifications. At the design stage, automated reasoning tools produce scalable architectures based on learned best practices. Implementation combines classical and quantum code generation, guided by contextual AI assistance. Testing leverages machine learning and quantum sampling to ensure reliability under probabilistic conditions. Deployment pipelines manage balanced distribution of workloads and quantum job scheduling. Maintenance becomes predictive. Analytic models forecast faults, while self-healing agents apply automated corrections. The result is a continuously evolving system that improves through experience, aligning with the vision of perpetual learning and resilience in software. Applications and impact. Engineering and manufacturing benefit from quantum digital twin simulations that enhance product design and reliability. The healthcare and life sciences sectors utilize quantum AI models for drug discovery, genome sequencing, and intelligent clinical decision support. Financial institutions deploy agentic systems for real-time risk assessment and fraud detection using hybrid AI quantum models. Cybersecurity gains strength through post-quantum encryption and AI-driven intrusion detection across hybrid infrastructures. Smart cities and environmental systems utilize multi-agent architectures to efficiently coordinate traffic, energy, and water management. These applications reveal software engineering as a catalyst for intelligent, adaptive, and sustainable technological ecosystems. Future directions. The next frontier involves developing quantum-native software architectures where quantum processes are intrinsic to the design rather than external components. AI-based verification of quantum code promises to reduce error rates dramatically. Global collaboration is required to establish interoperable standards and governance frameworks for hybrid software practices. Human-AI co-engineering models will enable joint creativity between developers, AI agents, and quantum processors. Education and capacity building remain essential. Future engineers must be fluent in both AI reasoning and quantum logic to fully harness these opportunities. Conclusion: advanced emerging technologies are redefining software engineering for the classical and quantum ages. The fusion of artificial intelligence, agentic automation, and quantum computation gives rise to a new paradigm, often described as intelligent quantum software engineering. In this paradigm, software is no longer a static artifact but a living, adaptive system capable of learning and optimization. The transformation marks a shift in both practice and philosophy, toward collaboration between human insight, machine intelligence, and the quantum foundations of nature. The outcome is a software ecosystem that is intelligent, sustainable, and transformative, powering the future of computation, innovation, and global progress.